We are doing the physical setting of physics. Tuesday, June 25th, 2019 exam.
Let's get it.
Question number 1. Which pair of quantities represent a scalar quantity? Well, let's define what a scalar quantity is. Magnitude only, which is just a number. Meanwhile, a vector is magnitude and direction.
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
With which we represent with an arrow. Magnitude is how long the arrow is, and the direction is the arrow tip. So which of these are a scalar? Well, v for velocity, v for vector, 1 is out. V for velocity, v for vector, 3 is out. Displacement. Displacement, you gotta look at where you start and where you finish, and then draw a line between the two. That sounds like a vector to me. Energy, we don't care about the direction. Time, clock doesn't tell you 12 noon north. 4 is our answer. Question 2, a sailboat on a lake sails 40 meters north and then sails 40 meters east. Compared to its starting position, its new position is, well, we take a look at a sailboat. We're just going to draw a line with an arrow. Hey, that's a vector. This is 40 meters to the north. And then it goes 40 meters to the east. Notice these are drawn tip to tail. I want to know where the new position of the sailboat is in relation to start and finish. This, by the way, represents my displacement, which is a vector. So to figure that out, we have a right triangle. Oh yeah, a squared plus b squared equals c squared. This gives us 40. Don't forget to square it. Plus 40. Don't forget to square it is equal to c squared. This leaves an answer of 56.7 meters. What's the direction? It's heading northeast. How do we know that? Because of our coordinate axes, north, south, west, and east. And you just match this up. That's northeast. Question 3. A ball is thrown straight up from the surface of Earth. Which statement best describes the ball's velocity and acceleration at the top of its flight? Well, let's look at a ball going straight up on the planet Earth.
Curious on why water balloons come straight back down after you throw them straight up in the air? Take physics.
Let's watch that again, but stop it at the top of the flight. What's happening at the top when the ball stops? Well, I just said the word, the ball stops, didn't I? So at the top of the flight here, we can say that the velocity is equal to 0 because the ball stops. However, what's the one thing that's always trying to bring the ball back down? That is, of course, gravity. This is F of g. The weight always points straight down. That's mass times gravity. So a little review here as well. Mass times gravity. Gravity is always acting on this object. Gravity, of course, is 9.81 meters per second squared. So the velocity is 0, but the acceleration is always 9.8 meters per second squared. So now we can answer the question. Both the velocity and acceleration are 0? Nope. The velocity is 0. Yep, that works. And the acceleration is non-zero. That works. The acceleration is 9.81. Choose your choice. Question 4. As a student runs a comb through her hair, the comb acquires negative electric charge. Well, the only possible way you're gaining electric charge or losing electric charge is by the transfer of electrons. Protons? Nope. Protons? Nope. Electrons? Electrons? Yes. Well, let's see here. The comb The comb acquires the negative charge, which means the comb is gaining electrons. Where did the comb get its electrons from? The hair. So the electrons from her hair to the comb. 4 is your choice. Question 5. How would the mass and weight, so we're talking about both mass here and weight. Well, let's review quick. Mass stays the same. Weight is mass times gravity. Fg for weight. So your weight is going to be dependent on your mass and your gravity. So let's see. How would the mass and weight of an object on the moon compare to the mass and weight of an object on the Earth? The mass and weight would both be less. Nope, that doesn't make sense. Mass has to stay the same. Mass would be the same. Ding, ding, ding. That works. Mass would be less. 3's out. Mass and weight would be the same. No, weight is dependent on gravity, and gravity of the moon is different than gravity of the Earth. 2 is your choice. The weight will be less because on the moon you have less gravity. Question 6. An object is moving with a constant speed in a circular path. We're talking about the object's centripetal acceleration here. Well, let's kind of draw a picture and take a look at what's happening. We are moving in a circle, and since we are moving in a circle, this is my car moving in a circle. And since this car is traveling around the circle, let's just say it's going clockwise. Problem doesn't tell us, but let's just say that it is. Well, the only reason it's going clockwise in a circle is because there are two things happening. First, there's a centripetal acceleration that points to the center of the circle. There's another thing called the centripetal force that goes to the center of the circle. And if the car were to all of a sudden not have the centripetal acceleration or force, it would go off in what we call a tangential velocity. So what's happening to the centripetal acceleration? Centripetal acceleration is v squared divided by r. Where do I get that? My reference table. If we look here on the reference table, we have two equations with a c. This stands for circular motion. In particular, centripetal. So centripetal force, centripetal acceleration, that's dependent on your velocity squared and the radius. Let's take a look. Well, the car is moving with a constant speed. So since the speed is constant, and it doesn't tell us that the radius is changing, this is constant, then when it comes to the magnitude is going to remain constant as well. So yes, this works. The direction doesn't work. So anything with the direction, no, all that's gone, doesn't work. Magnitude only. So the acceleration is going to be the same, the direction is different. Why do I say the direction is different? Because look at which way these arrows are pointing. Let's pretend they all represent the acceleration of the object. Here, the acceleration is pointing down. Here, it's pointing to the left. Here, it's pointing north, and here, it's pointing to the east. So the direction is always changing, but the magnitude or the number remains constant. 1 is your answer. Question 7. In the diagram below, a rope is attached to a 500 kilogram crate, and it's used to exert a force of 45 newtons at an angle of 65 degrees above the horizontal. What's the horizontal component of the force? Well, what I always like to do first is I always like to draw in my right triangle. So I'm going to draw an arrow here, and I'm going to draw an arrow here. There is my right triangle. This is my force in the y direction. This is the force in the x direction. I am looking for, in this particular problem, the horizontal component of the force. So all I care about is the x direction, so I'm going to use good old SOHCAHTOA to help me set up my trigonometry. Adjacent is what I'm looking for. I have my hypotenuse, so that is going to be the cosine of my angle is adjacent over hypotenuse, or the cosine of 65 degrees is Fx over 45 newtons. And this ends up giving you a force of 19 newtons, or choice 1. Question 8. A spring with a spring constant of 68 newton per meter hangs from the ceiling. So let's draw a picture. I have a ceiling and I have myself a spring. And that spring has a spring constant, or K, of 68 newton per meter. And it tells us that we are hanging a 12 newton downward force. So there's some force or weight here of 12 newtons. I'm looking for how much is this spring going to stretch. Obviously, when you hang something to it, it's going to stretch. So I'm looking for X, or the stretch of the spring. Looks like I got to go to my reference table. When it comes to springs, there are two equations we're going to need. The ones with the subscript S, these are used for springs. Well, I know the force acting on it. I know the spring constant. From there, I can find how much it's going to stretch. So Fs equals Kx. The force on the spring will equal to K times X. The force here, in this case, is the weight, which is 12 newtons. That's the weight on the spring. My K is 68 newton per meter. And then from there, we can solve for X. And X will end up being 0.18 meters. Wasn't page 2 just a blast? Well, if you're ready, then go ahead and jump to page 3. Or perhaps get pumped up and watch the intro video. It'll make you say, let's get it.